What I'm going to be talking about now is advanced rendering techniques using ES 1.1 extension pack. So in my talk today, first what I want to do is just give you guys a brief overview of a demo that my team created for the launch of ATI's latest 3D handheld chip, the Imagion 23-8X, which fully supports ES 1.1 extension pack. And then what I want to do is walk you through a series of advanced rendering techniques that we did in our demo, including all the effects you see up there. And the idea is I want to present all these techniques to give you guys ideas of the types of things you can do with ES 1.1 and 1.1 plus level of hardware. So here are some screenshots from the demo. And I should also mention I have up here one of ATI's development kits with it running, and after my talk you guys are free to come up and check it out. We'll also have it at the booth, but I'm going to be showing movies of the demo during the talk today. So the idea behind this demo was we wanted to demonstrate ES 1.1 plus. We tried to use nearly all of the features of the API. In general, we also attempted to minimize CPU calculations to use effects that would be realistic on an actual handset that supported this level of hardware. And ultimately, the goal, aside from showing off our hardware, was to provide techniques for game developers to use in your own games on this class of OpenGL ES device. So the first demo that I'll talk about is the lighting demo, and here's a screenshot from it. So some of the techniques that we used in this demo, basically what we were trying to showcase were per pixel lighting techniques that you can do with fixed function ES 1.1 and 1.1 plus. So we're doing per pixel diffuse lighting with .3 bump mapping. We are performing per pixel projective spotlight for fall off from the light frustum. We're also using a cube map to approximate per pixel specular highlights on the trash can, and additionally are using a stencil-based shadow technique. So let me briefly flip over and show you a movie of this demo. And this is basically a capture of the demo running on our Imagion hardware. Crank up the contrast because it's a little dark. So as you can see, we basically are doing per pixel .3 on the walls and on the trash can. You can see the specular highlight from the cube map on the trash can, as well as the shadows being projected onto the walls and floor. And additionally, the entire scene has this projective spotlight technique. So what I want to do now is actually walk you guys through all of the different lighting techniques that we used in this demo, and I'll basically walk through each step of the lighting techniques and talk about some of the issues and how we accomplish them. So the first technique, as I mentioned, is the .3 bump mapping, which is basically using the texture combined to do per pixel diffuse lighting. We have a spotlight using projective texturing. We then apply a specular cube map to the trash can. Render shadows both onto the floor and to the walls. We finally blend in a base map to give us the final image. And now I'll talk about each one of these stages individually and what some of the techniques were that we used. So the first stage is the .3 bump mapping stage. So I imagine many of you in the audience are already familiar with what .3 lighting is, so I'm not going to review that. But what I want to talk about are what the challenges are for using .3 lighting with ES 1.1 plus. So in general, when using ES, we want to minimize CPU calculations as much as possible and offload all of our calculations onto the GPU. The problem is that the typical technique that's used for using fixed function .3 bump mapping is tangent space bump mapping. And this technique, basically what you have to do is transform your light vector from world space to tangent space at every vertex. And this requires a matrix multiplication on the CPU. Additionally, it requires you to dynamically update this vertex data and send it over the bus to the GPU every frame. This is clearly not ideal for handheld. We really would rather be able to cache everything, but it's just not possible with what's specified in 1.1 plus. So basically, you have two choices to how to create your normal maps. Either the first way, which I just discussed, is you store your normal maps in tangent space, and you're going to have to perform this matrix multiply and use dynamic vertex data. The benefit to this technique is that the objects can freely animate, and additionally, you might end up using less texture data because you can use the same normal map on polygons oriented in different ways in the scene. The other technique you can use is store your normal maps in world space, where you're actually storing the world space normal at each texel. And this doesn't require any per vertex CPU calculations because you can put your world space light vector into the constant color and blend that directly in the texture combine. The downside to this technique is it requires much larger texture data because you can't use the same normal map on differently oriented polygons. And worst of all, the object must be static. So what we did in the lighting demo was we used tangent space normal map on the low poly surfaces where there would be less of these matrix multiplies, and a world space normal map on the high poly surfaces. So basically, on the walls, we have one tangent space bump map. On the trash can, the artist authored a world space bump map. One thing I want to mention about this is that the 2308X hardware actually has a vertex shader, which we exposed through an extension, which would allow you to do this per vertex matrix multiply for the tangent space calculation actually on the GPU. We didn't use that at the time we wrote this demo. The extension wasn't ready, but it is there now. However, if you're working with the other 1.1 conformant hardware, you're going to deal with this issue of how do I store my normal maps and how do I minimize CPU calculations. So it's a little tricky to really get much out of .3 with ES. So the next stage that we have in our demo is projective spotlight, where we're basically have a 2D texture that we project onto the scene to simulate the fall off of the light. So the way we do this is we have a 2D spotlight texture image, which is just a static image with light fall off in it. And again, we apply this with projective texturing to achieve the spotlight effect. So basically what we do is we send in the XYZ position of each vertex as a texture coordinate into ES. We then compute a texture matrix that is basically going to transform that position from object space into the projective view space of the light. And that texture matrix is composed of the three matrices here. We have LV, which is the model view matrix from the light. We have the projection matrix made from the light frustum, and then a bias matrix that transforms or that moves the coordinates from the -1 to 1 range to the 0 to 1 range. So basically, we compute this texture matrix on the CPU, and we send in these XYZ coordinates as texture coordinates, and then let the GPU do the transformation for us. What you end up with if you just do this technique that I've mentioned is this artifact known as back projection, which, for those of you familiar with projective texturing on desktop hardware, you've seen this before. What happens is when the coordinates go behind the light near frustum, you end up with this sort of symmetric spotlight where behind the light frustum you have a second spotlight, which is really not correct and not what you want. So the way that you resolve the back projection is what we want to do is we want to bind another texture to the second texture unit, and we want to fetch a value of black behind the light near plane, a value of white in front of it, and then multiply the result of that fetch with the projective spotlight to mask off the region behind the light near plane. So the solution that we use to do this is we create a texture matrix that computes the distance to the light near plane. We then use that distance as a texture coordinate to fetch into a very simple texture that has a value of black at 0, 0 and white at 1, 0. So the way that we compute this texture matrix is pretty simple. Basically, we have the plane equation of our light near plane, which is composed of a unit normal and a constant, which is placed in W. We place this in the first column of the texture matrix, pass in our XYZ again as a texture coordinate, and if you work out the math, this matrix multiply ends up evaluating the distance to plane, a distance from point to plane equation. So that gives us a texture coordinate to fetch from this very simple 1D texture, and we combine that with the spotlight texture. And so what you see on the left is there's the original image without the back projection fix. On the right is the image with this back projection, which we can do the combination of the spotlight and the mask texture all in a single pass on our hardware because it has dual texture. Oh, sorry about that. Okay, sorry. So the next stage we have is the per pixel specular cube map. So this is a pretty simple technique. Basically what we do is we just have a cube map with a simple light fall off in one of the cube map faces. We use the reflection map texture coordinate generation method that Afi mentioned in his talk, which basically generates an eye space reflection vector based on the normal and the eye vector. We then generate a texture matrix based on the direction of the light, and we use this to rotate that eye space reflection vector into the space of the cube map. Additionally, you can optionally attenuate the specular by a gloss channel on another texture unit. We didn't do that in this demo, but we did in another one, which I'll show later. So finally, the last piece is the shadows, which you can see rendered on the floor and the wall. So ES 1.1 Plus does enable true stencil volumes if that's what you wanted to do. The only thing about stencil volumes is that you have to do the extrusion of the silhouette on the CPU, which is, again, not really a very practical technique for a handheld device with a low-powered CPU. So we demonstrate in this demo a pretty simple technique. Basically what we do is we compute a matrix which we call the squash matrix that basically squashes the geometry we want to shadow onto the plane we're shadowing. We then use the stencil buffer to mask off the region we're casting the shadow onto. And also, as soon as we write a pixel, we write a bit into the stencil buffer, or a byte, I should say, that tells us to not write that pixel again. And basically, this makes it so you only get one layer of shadow. If you didn't use the stencil buffer, you'd end up with this sort of multiple layers of squash geometry. So admittedly, this technique is kind of only applicable really where you have a flat geometry that you're shadowing on. You need a more complicated technique for a general purpose scene. But we just wanted to kind of showcase the use of the stencil buffer. All right, so that's the lighting demo. I'll talk next about the water demo. So the water demo demonstrates a variety of reflection and refraction techniques. We have a cube map reflection on the pool of water. We're also dynamically computing refraction for this liquid in a closed container. We are also using frame buffer objects to do dynamic planar reflections on the floor. We basically have puddles on the floor which we're dynamically rendering with a frame buffer object. And we also apply static light maps to the scene. So let me quickly flip over and show you the movie of the water demo running. Again, I'll crank up the contrast. So you can see that the water is reflecting the scene, as well as there's refraction on the container. It's a little bit difficult to see on the projector, but there's puddles along the floor which are dynamically reflecting a reflection texture. So I now want to walk through all the stages of the water demo. So the first one is refraction and reflection. So first I'll talk about refraction mapping. Before I mention anything about that, let me just talk a little bit about how we simulated the water. Basically what the water is just a very simple lattice of vertices, and we run basically sine and cosine waves against each other to kind of simulate the look of water. The algorithm that we use for rendering the refraction is really independent of this technique. We just chose a very simple algorithm because we wanted to minimize CPU calculations. We then dynamically compute the refraction on the CPU. Basically what we do is we generate a normal at each vertex in the lattice, and we use the eye vector and normal to generate a texture coordinate that can be used to fetch into a 2D texture map. And I'll show an image of that in a second. But if you're interested in this technique, this is exactly what was described in the first game programming gems, refraction mapping for liquids and containers. So for more details on that, check that article out. So basically the refraction texture is an overhead view of this closed container, and we're dynamically computing the 2D texture coordinates for it on the CPU. In addition to rendering the refraction on the water, we also, in a single pass, render reflection. We do this with a static cube map. Basically, we pre-render a reflection cube map from the center of the scene by creating a camera with a 90-degree field of view and an aspect ratio of 1, and we basically have this static cube map of our scene. To apply the cube map to the water, we again use reflection map texture coordinate generation, and this generates us an I-space reflection vector. The thing about that is that what we actually want is a reflection vector that's in the same space as the cube map, which is in world space. And this is kind of a key point I do want to mention. If you are going to use cube maps for reflections with ES TextGen, you're going to need to use this technique I mentioned in a second to transform your generated reflection vector from I space to world space. So basically the way you do this is you take the model view matrix and invert it and load the upper 3x3 of this into the texture matrix. So again, if you're going to use cube maps and reflection map with a moving camera, you're going to have to use this technique. A lot of the SDK samples that you'll see out there that use cube maps don't actually move the camera, so you don't have to deal with this. But for a real game, you would need to do this technique. So just a little bit more detail. Basically what we're rendering is this 2D refraction texture combined with the cube map reflection. And ultimately, we also compute a Fresnel term on the CPU based on the view vector and normal. And we then get this final pool of water. So the next piece of the water demo I'll talk about are the dynamic planar reflections. So the way we render these are we create a frame buffer object to use for render to texture. And essentially what we do is we use the standard technique for rendering reflections. We flip the camera about the ground plane. We also invert the cull direction and draw the whole scene into this reflection texture. To render the reflections on in the puddles, what we do is we, again, send the XYZ position of each vertex in as a texture coordinate. And just like we did for the lighting demo, we compute a texture matrix that now transforms that position from object space to projective view space. So basically, you use the model view and projection matrix and that same technique we used in the lighting demo to generate this texture matrix for doing the projection. To render the puddles in a single pass, what we do is we bind two texture maps. On texture unit 0, we have the base map, which has sort of the rock color pattern and the base color, and the alpha channel holds an opacity for the puddles. We then bind that frame buffer object on texture unit 1, and we use the texture environment to combine these together in a single pass, where we're essentially masking off the reflection texture by the puddle opacity. So that's the water demo in a nutshell. The next one I will talk about is the post-processing demo. And the idea behind this demo was we wanted to simulate the effect of light bloom using frame buffer objects purely with fixed function processing. We also used diffuse vertex lighting to light this animated plane, as well as light maps for the soft lighting and shadows. So let me flip over and show you this one. So as you can see, you basically get this light bleed from this very bright window where the light bleeds onto the plane and all of the surrounding surfaces. And we're doing all of this work on the GPU. Additionally, you can see the light maps giving you the nice soft shadows on the floor, but they are static. So what I'll do now is describe the algorithm that we used for the light bloom. Basically, what we do is we create a frame buffer object, and we draw our scene. First, we clear that frame buffer object to white, and then we draw our scene in black. We then create 4 more frame buffer objects at sizes decreasing by a power of 2, and we downsample from one to the next using standard bilinear filtering. So basically, we're binding the 128 as a texture and rendering to the 64 by 64 just on a full screen quad using bilinear filtering. And you get this progressively blurred texture. What we then do is we bind 2 at a time these frame buffer objects, combine them together using these percentages, which can be tuned based on how much light bloom you actually want to get this final blurry image, which will ultimately be drawn on a full screen quad and added to the scene, which gives us the light bloom at the end. This slide here really just describes in words the algorithm I just described, so that's in the slides for reference, but I'm not going to go over it again. So the next demo I'll talk about is the skinning demo. And for those of you familiar with our Ruby demos on the desktop, this is Ruby's hand. We took it from a model from our PC demos. And what we're demonstrating here is the use of matrix palette skinning. So this hand is composed of 20 bones. Each vertex can be weighted by up to 4 weights per bone. And it's composed of about 5,700 polygons. We also use the per pixel specular cube map technique that we used in the lighting demo to light the hand. And additionally, we apply a gloss channel so that we can render these 2 different material types all in one draw call in a single pass. So let me show you the skinning demo. For those of you who read sign language, it's Ruby signing ATI Imagion 3D. And no, there won't be any vulgarities. So what I'll do now is describe the lighting technique that we used for the skin model. And I want to mention this because this basically what I go over here is typically how you would want to light a skin model using GL. I think we kind of came up with about the best technique you can do on a dual texture system in a single pass. So what we do is we use standard GL lighting for dynamically lighting the diffuse component at each vertex, and we use a directional light for best performance. We then apply a specular cube map to kind of fake this per pixel specular highlights, just like we did in the lighting demo, and we combine them together in a single pass. So what we do is we bind on texture unit 0 the base map, which has the hand texture, as well as a gloss channel, which has a different gloss value for the skin versus the leather. We then bind the specular cube map to texture unit 1, which is just a very small alpha texture, just like in the lighting demo I showed earlier. And we then configure the texture environment to compute this lighting in a single pass. So just pictorially, I'll show sort of what each step is, although this is all happening in one pass. So this is just rendering the base map. This is the hand with vertex diffuse lighting. And this is finally after we apply the specular times the gloss channel. And we were able to get pretty good performance using this technique. So the next demo I will talk about is the particles demo. And this one was used to showcase the use of point sprites and the distance attenuation to attenuate the point sprites by distance to eye. We also used a very simple technique to kind of simulate the effect of fire. We have this static light map that we attenuate by a flicker term that we're computing on the CPU. So let me quickly show you that one. One doesn't lend itself too well to the screen up there. So basically we have this particle system for the fire, and it's composed of at most 100 particles at a time, and they're all being rendered with point sprite primitives. So the particle system that we use for this demo is pretty simple. We just have some very generic particle emitters that are able to emit particles, in a spherical radius, or actually in a circular radius with various different properties. And we modify the properties over the particle lifetime. We modify the position, the color of the particle, and its size. And this work is all done on the CPU. And as Afi mentioned in his talk, ES allows you to attenuate each particle or to set a particle size for each point sprite. Desktop OpenGL didn't allow this, but we use this to have different sizes for each of the point sprites rendered. Now, point sprites are a nice technique, but they have a lot of limitations. For one thing, the texture coordinates that you use for the point sprites have to be this 0, 0 in the upper left corner and 1, 1 in the lower right, and you really don't have any other control over that. Also, the size of the point sprites are expressed in screen pixels, which means that you need to have a way to attenuate these points by distance to camera, and you do that using the point parameters function, which basically allows you to attenuate the particles. Also, because the size is expressed in screen pixels, you can also use this equation to account for different resolution sizes. So the way we use point parameters in this demo, well, I guess first I should review the equation. Basically, what you can set in GL are these three constants, A, B, and C, which are inputs to the distance attenuation equation. The value D is computed by the GL, and that's the distance to the eye. And then you can control how the attenuation works by setting these three constants. So what we do in our demo is we compute a scale based on the resolution we're rendering at, because this demo runs at QVGA and VGA. We square that scale and put it in A, and we also compute sort of a fudge factor of 0.15 times the scale and place that in C. And the way we came up with these constants is we have two rendering paths in our demo, one that uses point sprites and one that uses a quad that's screen aligned on the CPU. And we basically kind of played with it until they looked the same at different resolutions. There may have been some more rigorous mathematical way to do it, but it seemed to work. So this gave us a proper scaling by resolution change and distance to eye. So these techniques for point sprites are something you want to keep in mind if you want to use them for particle systems, because they're not all that flexible, but they are fast, so they're definitely worth using. Okay, so the last demo that I'll talk about is the reflection demo. And this demo was created to showcase the use of dynamic cube maps using frame buffer objects. We also have some very simple alpha blended shadows, and we use dynamic diffuse vertex lighting on several objects in the scene to make it appear a bit more dynamic. So if you take a look at the sphere, as this train circles around it, you can see that the sphere is dynamically being reflected, the train is dynamically being reflected on the sphere. And we're accomplishing this using dynamic cube map rendering. So basically what we do in this demo is we create 6 frame buffer objects, one for each face of the cube map. And then what we do is every frame, we actually render the entire scene into each cube face. Well, I shouldn't say the entire scene. We use a frustum culling technique so that we're only rendering those things that are visible to each of the cube map faces. We also had the artist author some proxy geometry. Basically, they have sort of like a stripped-down version of the train and the scene with less polygons. And this is done for performance. This is a pretty typical technique. We do this in our PC demos as well, where you really don't need the same kind of detail in your cube map reflection that you need in the real scene. And as I mentioned, we use bounding box frustum culling to cull out that which isn't visible. So to apply this dynamic cube map to the globe, we use the same technique as in the water demo. We use the reflection map texture coordinate generation method. And again, this technique to use the texture matrix to rotate from eye space to world space. In order to get the glossy appearance of the globe, we also blend it with a base map and use dynamic vertex lighting, which blended together gives a nice kind of glossy reflective look. So that is the 23.8x rooms demo in a nutshell. And to summarize, ES 1.1 Plus clearly enables a lot of advanced rendering techniques. I've showed you many of them. To kind of wrap things up, what I want to say is that you can really differentiate your game using these advanced features. And as ES 1.1 and 1.1 Plus hardware becomes more prevalent, you're going to get the kind of visual quality we're showing in these demos on real handsets. And I think that's pretty exciting. But that said, you really do need to think a bit differently to do these kind of effects on the handheld than you do in the desktop. You really need to always be thinking about doing as little as possible on the CPU and offloading the work to the GPU because it can just do a better job more efficiently and consume less power. the final thought is, get creative. By all means, these are just some examples of ES 1.1 Plus. There's much more you can do, and we really look forward to seeing what you guys as game developers develop for this level of hardware. So if you are interested in more info on this demo, on the ATI website, there is a white paper as well as the movies I showed and some screenshots. And that's about all I had, so thank you very much, and I'll open things up for questions. Could you step up to the mic? Thanks.
The implicit texture Do the implicit texture coordinates for the point sprites still go through the texture matrix?
No, they don't. I think that's right, Afi, right?
They do not go through the texture matrix.
That's a shame.
Yeah, so it's really difficult. Especially, I've noticed that a lot of developers will use page textures for rendering their particles, so they have to do less texture switches, especially if you want to do animation. Well, with point sprites, you kind of don't have that option because you have this fixed coordinate generation. So it's a little bit limited. Any other questions? All right. Well, thank you very much.